Hello, how are you doing? So, you decided to be stuck with me for the next hour or so. I hope you'll have fun. This is going to be a weird C++ talk, as there's almost no C++ in it. I tried that thing in Montreal for a C++ user group about 2 months ago. Crowd reaction was surprising. People actually liked it, which came as a surprise to me. It seemed to be a dry topic of sorts. But you'll see. So, who am I? Should you not know about me? Well, I have a few kids. I used to do military flight simulators. I have a significant number of animals due to my wife, who works with animals, so like 15 cats and a number of dogs and all that. I've been teaching for about 20 years now, 19 to be honest, and one of my peculiar clientele is the video game people. So I work with a number of games programming companies, well-known ones. And I work at university and college at the same time, so I teach a lot. One of the things I do in the standards committee where I am, others in the room are too, is I'm involved with SG14, which is the low latency study group, and a few others. But this is the one I'm seeing most often at. I'll be there on Wednesday. Should you all be there too, you'll be welcome. So, so you can ask questions wherever you want. It's probably simpler to wait a bit, but I'll catch you if you do ask something in the meantime. I don't mind. You can disagree with me, although I'm going to be reading standards text. So it's not going to be as exciting as Michael Case's reading last year or earlier this year. If you heard about it, he actually did a slam with it. That's what I'm going to do. So, and I won't have all the answers maybe, but I might have a few. So I hope it's going to work out for you guys. So as I said, I'm a very terrible PowerPoint user. This one has way too much text, but still. So when you're writing a program, you tend to be thinking, oh, okay, I'm going to be using this feature, I'm going to do. And people tend to think in terms of, okay, I'm going to be passing my variables there, they're going to be on the stack, I'm going to be this and that. And they work for some kind of machine that they have in their hands, which is not the machine they're really coding to. They're coding to the abstract machine. If you look in the standard doesn't care about the same things you do. It cares about a very peculiar, very different set of considerations that people who work with actual hardware do. So the purpose of this talk is for people who are not aware of that to get better acquainted with the machine they're actually writing programs for. This is the one that you're going to run programs on, but it's going to influence what you do. So this is essentially what's written there. So to provide a practical overview of what that abstract machine is and how it affects the way you code, or maybe you should code. The number of people I get in the room with me who are telling me, this is the way things work, I'm telling them, no, it's not. It's the way your compiler is doing it. But it's not what the standard says. And what you're writing might work like that way today. It might not work the same way tomorrow. Or if you change compilers, you might be in for a few surprises, so you better be aware of it. So that's the goal. So there's a plan there, which I will skip, but you can read it if you have time when the thing gets published online, but that's pretty much what we're going to do. So there. So what is an abstract machine? It's not the same thing as a virtual machine, at least in most people's view. I tried to look around on the internet to see what people were saying about that. There seemed to have been a few discussions 2 years back. So there's this guy there, Zubkov, who's a nice guy, and who's here in CppCon. He has a talk later on today, if I remember properly, who says something like, it's the simplest imaginary computer that can actually run a program that you wrote in the source language, or in a set of languages, when he was referring to the JVM, where there's a number of these running. So that's one point of view. It's a simplification of the actual hardware that you can actually write programs for, in your mind at the very least. There's this person I don't know, whom I don't know, who said, well, Seminole, which permits step-by-step execution, and we design programming languages for a range of targets, and this kind of abstracts the details of the actual hardware. Why not? Okay, so you're not writing for a specific architecture, you're writing for something different. It enlarges your vision, in a sense. There's this other person who wrote on Wikipedia, so I have no idea who that person is, who said, well, it's a theoretical model of a computer that you can use in theory, I guess. Okay, very general terms. Why not? People probably use that. He said not to be confused with virtual machine, because these are actually big beasts that do very different things. The .NET one, the Java one, they're very different. And there's this somewhat long text, but that you can read if you want to read the slides afterwards. It's a very nice text from Mr. Morteray, who's the author of A Leaf Language, who makes a very nice case of why you would need or want an abstract machine, saying, well, your program is instructions really, and you don't want to write your program for a specific piece of hardware. You want to write it in a general way and transpose it to the actual hardware at some point. So it's a very useful tool for thinking to have an abstract machine, something that you write for that's not tied to a specific set of registers or this kind of memory or that kind of memory or this kind of I/O. Elevate the discourse a bit. And he adds at the end, and I used to say rightfully, but someone in one of the rooms where I gave this talk before said, rightfully, I disagree. Saying, well, in academia, Turing machines and lambda calculus are examples of abstract machines. So there are some people who disagree with Mr. Morteray in this case, but it's a point of view. So the one we have in C++, taken from one of the texts that Bjarne wrote about 10 years or so ago, well, it said, we're using C++ in a lot of application areas, of course. It's part of what he said this morning. I mean, an interesting thing about C++ is what we can do with it. So how do we do that? Well, we try to add an effective abstraction layer. We try to have zero-cost abstractions as much as we can. And we're not writing for a specific piece of hardware. Of course, it would be very inefficient. So we try to map directly onto hardware as much as it's reasonable to do so. So we have basic types that tend to map to very specific entities, bytes, words, or so. Our pointers represent contiguous address model of memory that we borrowed from C. Why not? There's no abstract mathematical model that gets in the way between what you're coding and the actual hardware. So we tried to make something that's very thin, such that you can actually reason on something that really looks like a real machine, even though it's not. So of course, you have to be careful because the mapping of types of hardware, it doesn't always map in the ways people expect. So a char is a byte, although we have a 3 byte now, which you might have noticed with C++ 17. But an int is not necessarily a register or the same size. Could be different, so you have to be careful with that. And we do borrow a lot from C with this. The idea is we can express a cache, memory mapping unit, ROM. We will not necessarily go there. We can express it if we want to. We can get close to the hardware, but we don't have a machine that says you have a cache. That's not what we do. So there's another guy named Chisnall whom I don't know much. We gave a really nice introduction to the C abstract machine, saying that, well, things like language constructs tend to map to machine instructions very closely, which helps you to think in terms of the efficiency you're going to get. It's working very hard in C to avoid things that cost you something, which brings us to the zero-cost abstraction model of C++. You don't have a garbage collection because it could cost you something. You don't bounce check the arrays because it would cost you something. You can do that if you want, but it's not something we do for you. It's something that you pay, should you want it. You have your memory in C that's exposed as an array of bytes, essentially. That's what you think of it. And you think of it as a flat array, although it's not always exactly what's going on in real life. You have typed addresses, so you have pointers of something, and you can reason in terms of arithmetic based on that. And it's simple and sufficient, it works. I mean, it lets you think about things. Alex Stepanov has written text about that at some point, also praising that model. It's simple, it's efficient, it maps well to higher level concepts like iterators and others. So there's a lot to be said about that, even though some people complain, of course. So we have this big beast named the standard that says things about the abstract machine that defines the rules and the playground for us. So without much of a surprise, it appears early on in the text. So in the first pages, you will see most of the meat of what's going on here. If you've never read this beautiful piece of literature that's the standard, the first few hundred pages are essentially maintained by a group named Core, of which there are members in this room, including me. I tend to spend my life there because I really like it. And the higher pages are essentially library playground, and in between, there's not much. It's pretty much these two working groups that write the paper, and you'll see differences in style. Now, core has been said to be dry. It also has the most beautiful examples for those of you who have a very twisted mind. So if you look at the very beginning of the document, you'll see things like what you see up there. I tried to put emphasis on some of the pieces, and the links that you see, yield.is, they're officially maintained now by the ISO Standard Foundation. So we can actually say that they're real excerpts from the standard. You can actually use that and be confident that it works. So if you click on these, which I won't because my internet connection is shaky a bit, you will see the actual excerpts from which I'm picking up the stuff. They might slightly differ from what I've put there because I did these slides in February. I did them in June based on the February text, and there's been an update in July, but it's very, very close. I don't think anything has changed, but I didn't verify every single word. So this one says that it's standard text is dry. We define a parameterized, non-deterministic abstract machine. Non-deterministic tends to make people react. I'm actually writing things. There's a specific meaning for that. We'll come back to it. So conforming implementations have to emulate the observable behavior of the machine. So you're writing things in terms of that abstract machine which doesn't exist, and your compiler has to transform your code in such a way that it behaves as what you wrote. It's pretty cool as long as you're following the rules. You're feeling better now. You're writing for a non-deterministic machine, aren't you? so there's this provision that says, we call it the as-if rule with quotes. You know? Everyone refers to it. It actually has a name. It actually exists. And what it essentially says is that the compiler can do a number of transformations that would hurt your heart if you saw them. Because you write your code with care and with love, and we don't care. But we're going to try very hard, not we, the vendors will try to work very hard to keep the observable behavior of what you wrote. If you follow the rules, they're supposed to keep that for you. So it's as if they did nothing, except that it works faster and better and everything. So parameterized and non-deterministic in a very specific sense, which is essentially what I just said. So that means the program can not do things that you wrote if the compiler judges that there's no point, that there's no observable behavior tied to that. So I put a link there, but normally I would click on it. But since my internet connection is shaky, I cheated and I used Matt's, who's in the room, tool there. Writing this thing, it's a very, very bad piece of code, okay? But I use it very often. I have students who come into my class, especially when they're beginners, and who ask me this very deep question: should I use while, do while, or for loops? Which one is faster? The first time my arms just fell, but then you have to remember that people who start, they have no idea if this makes sense or not. They are really worried, and they want to sound efficient, so they're wondering what kind of loop they should stick to and forget all the others. So the fun thing is you write the code. I wrote a program that accumulates, essentially, numbers from 1 to 10 in 3 different loops. And you write that thing, and you show them, and they see all of this code. And if they look at it, they say, oh, yeah, there's an additional jump somewhere in the for loop because you have to step over the incrementation and everything. Why not? So they look at this and say, first of all, loops are very expensive. There's a lot of code there. Yep. And then you add something. You optimize the code. As you can see right now, there's no optimization. There's no level optimization whatsoever. And when you add O2, it's much nicer. because they're not noticing, of course, that you're not doing anything with the computation you did. So you're just computing things and never displaying or saving anything. There's no I/O. There's no observable behavior to your program. So it's pointless. Almost like the question was pointless. So this shows, kind of like Bjarne was doing this morning, if you're not optimizing your code, you get what you deserve. But if you do put on the optimizer sometimes, well, you realize that the as-if rule lets the compiler say, oh, pointless. So this is perfectly legal. You don't have to stick to what you wrote. The compiler doesn't really care as long as there are rules and they're being followed. Another one is that I've heard from colleagues, so people who've been teaching for longer than I have, for more than 20 years. Like, I want to do a find on a vector, and I want to do a find on a set. And I've been told that vector is very fast. So I'm doing linear search, but people say the cache, blah, 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 blah. And yeah, depending on what you're doing, sometimes one is better, sometimes the other is better. So they come to me with something like this. I did a vector find and I did a set find, and I used Fred, I think it's Tango, his benchmarking tool. Hey, nice tool. Glad to see you. It's very nice. So, and there's a poster about it downstairs if you want to go through it. So this very small thing that essentially does the same thing in terms of conceptual stuff, inserting the same number of numbers from 1 to so, and then doing a number of finds in both cases. And of course, if you did it like this, vector seems to be very slow. And obviously, since optimization is 0.1 in this case, you get what you deserve, because if you change the optimization level, you get something different. The set's not faster or slower, it's just that compiler noticed stuff. And probably in this case, the set is doing more memory allocation, which could be observable, I guess. So there's something costly there going on. Whereas in vector, well, not much. So you have to be careful with that. So the as-if rule plays a role. It does, you enjoy it, and as long as you're careful with it, it's pretty nice. So what is an observable behavior now? Well, you have side effects there. I/O from the library, something that calls such I/Os. You read an object that's volatile or something. So yeah, that's it. That's what you have to pay attention to. If there's none of that, your code might go away, but you didn't need it in the first place, did you? So it's very powerful and you want it. You have to be careful when you have more than one thread, you have shared state. You have to say explicitly what you mean. Otherwise, the compiler might assume stuff like there's no threads. Yeah? And I've been reminded by people, you can have empty programs and with only 2 instructions if you look at Godbolt, and they're much bigger when you run them. It's because there's libraries involved and you link with them and so. Depends on your quality level. You have to be careful with your assumptions there. And so there's assumptions that you might have that are not necessarily true. So you have implementation defense stuff like the size of an int. The number of people believe this is 4. We never say that. No. And I've been taught myself, size of int is the size of a memory word. I held that as belief until I actually read the text, and we don't say that. It tends to be that way. We tend to, for historical reasons, to want the short name type int to be the fast one. But apart from that, And the size of some t, which might change, even in some compilers, size of string, depending on your optimization level, you get different numbers. Why not? You can count on the size of char being 1, but that's not 8 bits. It's probably 8 bits now. So there, these implementation-defined little things, they constitute the parameters of the abstract machine. We had a very interesting presentation in Toronto this year by Lisa Lippincott, whom I haven't seen. I don't know if she's here this week. She was here last year. Very interesting thing where she used, I put a reference if you want to read about it. She used the abstract machine as leverage to make programs more resilient and make reasoning about assertions stronger. Very deep things. So she used that thing, and she actually modeled the abstract machine as a machine using these as parameters. Very interesting thoughts. You have also, on top of the implementation-defined stuff, you have the unspecified stuff. There are things we don't say. People assume things. So when you have a new expression with many arguments, in which order are they done? Well, we don't say. We don't say. Especially if we fail to allocate memory, we don't say much about that. So if you have beliefs, that's fair, but who can say? So these things are funny because your compiler will do something. You just don't have any portable assumption as to what will be done. So this is what we call in standardese the non-deterministic aspect. So it's not as bad as it seemed. If you stick to a specific compiler, you'll probably get stable behavior, although you cannot count on it. So they are doing something, it's fair, It's not dangerous, but the assumptions on which you base these are non-portable. You don't see it, but I'm sorry. My little thing there as a word on that, there are people who want to fix an order to evaluate, when we evaluate sub-expressions of a given expression, and there are levels to which I personally would stop, and there are things that I think are fine. There are philosophical arguments about that. But these things that are reasonable but depend on the implementation, they exist. So, and there are undefined things which you might have heard about. These are things of evil. And so modifying a const object, doing all kinds of evil casts. Well, if you do that, I'm not even sorry for you. So we impose no requirement on programs that behave that badly. So you're on your own if you do that. It might work. So a conforming implementation that executes a well-formed program will produce the same observable behavior, blah, blah, blah. However, should you be an evil person who has even one of these undefined operations, well, we place no requirement, even if the operations that are evil are below and the code above seems nice. We don't care. If you do that, you decided to go on your own playground and have fun. I didn't put a link to that in the presentation because it's not a talk about undefined behavior, but there's this very nice tweet we had a few weeks ago that made us talk among ourselves, where someone had written the function, some people are already doing that, who did rm minus rf on a function that's never been called, and the generated code calls it nonetheless because someone is accessing an old pointer. Don't do that. It's very easy to do things like that, and you'll get bitten. And I've been reminded by some ISO people from other groups, the safety languages, the safety programming languages groups or so, that if you're using a standardized language like C++, you're actually liable to get sued or stuff like that if you're going that direction because you're expected to be an expert doing reasonable stuff. Now, some companies will hire you because you're writing using a standardized language. So please don't do things like this. So we have some rules tied to program execution. That's very nice. RAI, the idioms like that, they're actually they're not named like that in the standard, of course, but they're part of the execution model. So you can see that. There's a link with the closing brace and some code being executed. You can count on that. It's reasonable. It makes sense. We define the rules tied to lifetime of your objects. That's standardized. You can count on that as long as you're following the rules, of course. And there's a number of other things that we mentioned briefly. So what happens when a program terminates, as long as you didn't break anything like throwing from an except function, IOs and everything. There's a set of things that are named and said to be the observable behavior of the program. So your implementation can be stronger. They can do more and ask more of you, but there's a baseline on which you can count. It's standardized. We define things such as the order of evaluation of expressions, how the operators, in what order are the operators evaluated in the complex expression. That's all standardized. We have these things that are very nice. The taxonomy of the expressions, it used to be so simple, wasn't it? Anyway. I almost feel bad showing that to people. I don't show that to students anymore because they freak out. So we have these generalized L values. That actually has a name in the standard and it's used as such. So object, bit field, whatever. The pure R values that we use when you have unnamed results from function calls or expressions or anywhere, that's pretty cool. The expiring values that will die. Sorry for those who have things in their ears. I had to do this because last year I did this and some people started complaining on YouTube that they were listening to my talk during the night. I hope they'll try this one. So there. And we have this amusing thing that's either a PR value or an X value. That's we call R value, that's old speak. And the old L value, that's a global L value, that's an expiring value or whatever. So we have all these categories because they play a role. I won't get into that. Main is special. There's a guy named Adi Shavit. I don't know if he's here this week. I think he is because I saw a tweet by him this morning. who tried to make a recursive main, and he was very, very happy that he was doing Fibonacci using main. It's illegal. It might work for a compiler, but we actually say, no, you shouldn't do that. You cannot call main in your program yourself. You cannot recurse on it. It should return an int. And there's a number of rules like to it. Main is special. So, and there's some leeway with the first paragraph that lets vendors play tricks on embedded systems to save space. But essentially, there are rules tied to main. If you return from main, you call exit. Program's over. So it's written. It's not something that people thought of like and started spreading rumors. Main is special. The function main shall not be used within a program. Its linkage is implementation defined. Blah blah blah. So you cannot have a context per main, as far as I know. So there's rule tied to that. Okay. So you cannot do anything you want. Gary this morning mentioned memory model when he was saying that he shows sometimes students how to write their own kind of vector. It's tricky. There are things that right now are hard to do when you're not in the standard library with that, when you write strings. And he was saying at some point you have to dirty your hands and touch the memory model in class, otherwise it remains magic, which is kind of true. Yeah? Unless you've touched that thing a bit, programming looks like magic. So we have bytes there. That's a fundamental storage unit. SD byte today, char before. And there's rule tied to byte. So if people are complaining, a byte is 8 bits, standard text there says, well, at least 8 bits, of course. Bytes have unique addresses, blah, blah, blah. That's part of the machine. You can count on that. Sometimes you want to compare unequal pointers to objects, and you're doing dirty things like comparing distinct objects and saying they're equal or something. So you have rules there if you're pointing to different elements of the same array, and if you're pointing to different non-static data members of the same object. And there's the last one there. Otherwise, neither pointer compares greater than the other. So you could actually have situations where you compare two pointers, and A is not lower than B, and B is not lower than A. And they're not equal, and you're confused. Confusion stems from the standard. You shouldn't do that. You're a bad person.
What happens? Can you compare less than, though, if it only says can't compare greater?
You should write an effect report for that. So this guy said just for the recording, if you're using something else than less than, what happens? Write an effect report, please. So the rules are there. Yeah, so the compilers can reorder your operations according to the as-if rule, and you like that. Your code will get faster in most cases. Be careful with multi-threading, as we said. And we're offering you guarantees, which essentially say that if you're playing nice with us, your code will be sequentially consistent. So you will look at the output. It will be reasonable based on your source code. As long as you don't have something called a data race, which is at least 2 threads touching the same object concurrently without synchronization, and one of these is doing a write, in which case you're way off in undefined behavior land, and we're not looking at you anymore. So there. And in the abstract machine, you'll see rules for that. Because, of course, you cannot write safe multi-threaded code if you don't have rules for these things, because the optimizer will pass by and disregard all of your presumptions as to what your code is. So you have synchronization operations. They're defined there. There's a modification order of objects in the abstract machine. Specific orders now. There's no requirement that you can totally order everything all the time. There are things that are really concurrent that could happen at the same time in a given program. It might make sense. Why not? But yeah, if you wrote the correct program, you look at it at the end, and you ask all of the threads what happened based on the order in which your writes to shared objects occurred, and they will agree. They won't agree beforehand, but they will agree afterward as to what happens. It's pretty cool. You can actually debug code when that happens, whereas you might not in other circumstances. So we have also in the abstract machine, tied to the memory model, a number of rules that the SG1 people could explain better than I do, but still synchronizes with, which says there are relations that describe how a write to a variable in a thread and a read from the same variable in another thread can behave depending on what you wrote. It's pretty nice to have rules about that. Sequence before, which says in which order things are expected to happen, or at least if there's a dependency between them. That's part of the machine. So if you're following the rules, you'll get reasonable behavior. Carries dependency, which I would not get too far in because it's tied to memory order consume, which is where we're still working on. It's not exactly as we would like it to be. But which says that if you have operations where the result of one is involved in the computation of another, we will not reorder things in such a way that we will break your code if we can avoid it. Thank you. We've got to have time at least. We have things like inter-thread happens before. It's pretty nice too. So there are ways to say what happens there will happen before something there. It's defined. So if you follow the rules, you'll get that. It's a pretty nice machine if you think of it. So when I talk to my games people and they come to me, I'll say, okay, that's fair. That's all very abstract. I don't really care. I'm doing real things. I'm doing real work. So what about a stack? I put variables on the stack. Where is that? Where are the rules about that? Interesting. There's no such concept in the abstract machine. So if you take the PDF version of the standards text, you look for the word stack, you'll find std stack, which is a container, an adapter to a container at least. You could go code it yourself. It's something fundamental to the machine. So, and for good reasons. I mean, we have things coming in like coroutines that might not be using a stack at all. As a colleague from SG1 told me, there are machines where you have more than one stack per thread. You can play with that. So the thought that some of us have, saying, well, you have a single stack per thread and that's where the arguments go, that's a per vendor thing. It's not something that the abstract machine describes. So yeah, if you look for it, you'll see stack unwinding tied to the behavior of programs when exception is strong. So the word stack is there, technically speaking. And there's a number of occurrences of stack in the section where the library talks about std stack. That's about it, to be honest. So it might be surprising to some who start with that assumption. So there. So others will say, okay, fair. So about my registers, I have these things that are as big as an int in my mind where there's actual work being done. So how does the abstract machine express this concept, this idea? Interesting. No, it doesn't exist in terms of the abstract machine at least. Doesn't mean your machine doesn't have a register. It just means that the abstract machine doesn't talk about it. Maybe it does, maybe it doesn't. If you look for the word register, you'll see the register keyword, which is unused right now. We deprecated its older usage, and then we removed it. And it will, I'm sure, come back in strength at some point once we've all accepted the fact that it's gone, because it's a very nice word to have. It's still reserved, but if you do register int for a loop counter because you're still living in the 70s, you might have some compiler options to set to make it work, because by default it shouldn't. So you have things. When an object of class type X, it's beautiful to read, is passed to or returned from a function if each copy constructor, move constructor, and destructor of X is either trivial or deleted, and X has at least one non-deleted copy or move constructor. Beautiful, I said. Implementations are permitted to create a temporary object to hold the function parameter of the result object, blah, 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 blah. And there's the word register in the note there. So there's one occurrence of the word register. It says, this latitude is granted to allow objects of class type to be passed to or returned from functions and registers. But that's what we call a non-normative note. So it's not something that's binding, it's an explanation. So should you be using registers? Well, you have leeway there. We're giving you some space. Aren't we nice? So yeah, non-normative, not part of the abstract machine, it's not part of the rules. So if you're writing a program and you want a correct program, you have to conform to the rules. It's important. If you rely on implementation-specific stuff or unspecified stuff, it's going to work. It will never be really broken, but your assumptions might not be met if you change compiler version or technology, depending on what you do. Most vendors can be expected to be pretty careful, I guess. So they won't break your code voluntarily, and they won't do unreasonable things. But what you wrote is not something you don't write life support systems based on that. and if you're writing undefined behavior using code, you're writing a time bomb. I mean, but anything could happen, and you deserve it, as I said. So this one is a nice one because I used that as an example last year in a class I was giving. I don't know if you, I don't, you won't see anything. We'll make it bigger. Give me a second. So I was writing this thing about atomic counters because we're discussing other things in the class I was giving. And there's these two threads there that are using an int concurrently without synchronization, incrementing it a number of times like this, and at the end returning the number of the value of n past the incrementations. So 2 times a million plus plus. And the same thing with an atomic int at the end, where we're returning n.load at the end because it cannot be copied. and people were saying, well, does that really make a difference? So we checked, of course. And if you run this thing, it's funny because you get, without too much of a surprise on that compiler, with a raw int, you get the wrong number, but very fast. And with the atomic int, the right number, but you paid something. And the degree to which you pay can vary from compiler to compiler. It can be up to 10 times or something, but anyway, you get the wrong answer in this case. and someone in the room was very, very nice, came to me after the class and said, I tried it, and I get the right numbers all the time. I get the right numbers. So why should I use atomics? Yeah, that's very interesting. I picked one box in this case because it uses a recent GCC, and effectively, if you run this code, it's the same code, I didn't show you, but it's the same thing code, raw int, very, very fast, and the exact correct number. Beautiful. And do you know what the difference is between these two, because I have the same source code? The second one does optimization. The first one was at no optimization level, and this one used O2. So what happened, which I think is a beautiful example of what we've just been saying about EUB, is that in the first case up there, we're doing concurrent writes to a common int in 2 separate threads. No synchronizations whatsoever. So we get undefined behavior. I mean, we're dealing with broken code. The compiler is very nice. He's guessing what I wanted to do. And he did it. I have a totally correct, wrong program. It's a thing of beauty. And it's extremely fast. So you could make a point saying undefined behavior is tremendous. It's making my code better. Or you could be surprised and wary and saying, can I count on that? Was that a right assumption? Probably wasn't in this case. So in this case, you're probably better paying for what you want because you'll get more portable results. Yeah? But it's fun. Change from compiler to compiler, and the way this thing is being processed changes. It's instructive. So yeah, the difference in the results, why were the atomic writes slower? Because they include synchronization, takes something. And if you want to have a very fast, correct program, don't use shared state. Increment local variables and add them to your shared state at the end, much faster. So if you use a higher optimization level like I just did, your results will vary. If you use, as far as this writing, if you use the Microsoft compiler, you'll get a very fast, wrong program. And if you use Clang or GCC, you'll get a very fast, apparently correct, but totally broken program. It's broken in all cases. In one case it shows, in the others it's hidden. So yeah, the code is very, very bad. And as I said, don't use shared state until the very end and then write to it only if you really need to. So how does this impact what we do with the standard and with the language? I know that because it's bitten me. I have another talk tomorrow where I'm going to talk about something I've been working on for a few years now. And I have a feature that my users need and that just doesn't fit. They want to specify the stack size of their threads. It's hard to do. We don't even have a stack. So we have to find a way to say what the users want without polluting the standard with things that the standard doesn't need, because it would be harmful to things such as coroutines that really don't need it. So should you want to write your own proposal for a standard, considering what we've just been skimming through, well, one of the things that you can do is restricting yourself to features that are actually part of the language. So if you're saying, I'm going to make registers access much faster, you're probably better off talking to your compiler vendor. They care about that. The standard doesn't much. We are going to do everything we can not to be in the way, but we are not considering what your specific architecture is doing. It's none of our business, really. Okay? Our job is to let the vendors write the best compilers they can. And should you want, as I said, to add something that doesn't fit really, really well, it's trickier because you have to find an abstraction that hides this in a way such that the standard remains clean, at least, of such considerations that would not be in the right place. And you have to ask yourself, will it add something? If you really want to speak about a hardware register in the standard, will the standard be better after that? Unless you have a very convincing argument to the effect, people will probably say no, and it won't pass. And then you'll probably be thinking, well, they're all idiots. Because, of course, everyone knows that should your proposal not pass, it's because everyone in the standard is an idiot, which I can confidently say it's not true. These people are actually pretty bright. So, for those who are interested and we didn't know about them, there's less and less people who don't know about them. For the comparisons I did, Matt-Godbolt's tool is amazing. For the benchmark, it's much younger, but it's very cool. Fred's stuff is very, very cool. And Tim Song's thing to explore the standard, even though I didn't link to it with the slides because my internet connection is bad, it's actually lovely. And you can actually count on it because it's officially supported. So really, really nice. If you want to quote the standard yourself or look at specific parts of it, it does highlighting and everything is very cool. So I used for my quotes the standard from February. There's a more recent one. Should there be discrepancies, they're my fault. The articles that I used as reference or as quotes are also in there, should you want to look at them. Interesting some of them. The talk by Lisa is there. I strongly urge you to read it. Lisa's a brilliant person, really. And I have my website where there's a lot of stuff, but it's in French, so some of you will say, ugh. Most of you will react like that, will react to the color scheme. Sorry. I don't see colors all that well. So there. What can I do for you? Did that make any sense?
Yeah.
Phew. Any questions? Comments? Threats? Hello.
Hi. So in a hypothetical universe where,
Of course.
where I actually have a compiler that's giving me a byte that is not 8 bits.
Oh, there are many.
There are.
Yeah. If you go to DSPs and other stuff, you'll get many of that. Yeah. If you're using general purpose hardware and you're running Linux, you probably won't meet them. But yeah, if you're using specific hardware, there are a number of these.
How do you deal with that? Like as a programmer?
There's a C programmer would tell you there's char bits in limits.h or C limits if you're in C++ that tells you how many bits there are in a char. So why would we have a macro for that? No? If this was a fixed thing. If you're in C++, you can use numeric limits, unsigned char, colon, digits. You want to use the unsigned one because the signed one won't count the signed bits and you'll get a surprise. You get an odd number of bits and that would be surprising, I guess. So the short answer to your question is most of the software you would try to use that is not aware of that would probably be broken due to the wrong assumptions that say, well, chars are 8 bits. Everyone knows that. Yep. And integers are 4 bytes. Everyone knows that. So it's my hope that if you're getting out of this room and you don't write such broken software, the whole world will benefit from this. That doesn't mean you shouldn't use the bits in your thing, but should you write something that is dependent on those assumptions, you should at least test them with static assert first. Yep.
So given that I can only count on observable behavior to actually happen in my program, and something that otherwise would look like a dead store to memory happens to be into a memory mapped file, should I always access my memory mapped files through pointers to volatile?
That's a very good question. It's probably, the thing is, for this sort of question, you probably have to look at what your vendor is providing. because memory map files are outside of the scope of the standard too. We don't have any standard ones, so we don't have rules for that. Compilers will be sometimes stricter as to what the rules are, so for their given platform. So the volatile rules for Microsoft, for example, were traditionally more stringent than what the standard actually said. Now volatile is very much underspecified right now. It's hard to use properly. So what you should check is what your vendor is providing for that specific tool and make sure that you're following the rules for that. Because until we have std concon memory map file, it's hard to answer that question properly.
Thank you.
Yeah. Oh, I still have 15 minutes to your question. Yeah, I was fast today. Yep.
Yeah, in your example, you told us that somebody was using an undefined behavior, but the compiler detected what it supposed the developer meant and meant something that kind of worked. I'm a bit scared when my compiler tries to determine what I meant. I've been an HTML developer in the past, and I all know that all problems come back from the fact that when you forgot to close a bracket, it just tries to guess what you want to do. Wouldn't it be better if you just throw a warning or an error or just refuse to compile? Why are they even doing that?
There are many answers to that. One of them, there are many other cases. JavaScript with the injected semicolons is another case. Go probably does things like that. So there are probably compiler settings that you can check because it's a per vendor kind of thing. You know, what we say in the standard is we won't say anything about your program. You're dead. To us, you don't exist. Well, you kind of exist. But, you know? We love you, but no. Another thing you can try, should you want to try it, is use context per functions, because you're not allowed to use undefined behavior in context per functions. So at least this will reveal some things that might not have been revealed otherwise. That being said, they're not all as strict as they should be with that. But should they want to be, if you're using undefined behavior in context per functions, that's supposed to compile at all. So that might be a nice trick. Yep.
All right, so this is more of a comment.
Sorry.
Yeah, so for example, when you were talking about C will do no array checking for you, but you also said that you can do that yourself. Yeah. And I have a comment about that if you think that in general C++ doesn't have enough defined behavior, well, you can use a library that defines it for you. If you're annoyed that int does not guarantee anything on overflow, you can make your own integer type, which throws an exception, wraps as if it was to its complement, and you can get basically Java in C++ if you just rewrite all the behavior of the Java virtual machine on those things. So really, some people would like to see all the undefined behavior gone from the C++ standard, but if you have a behavior that works well for your platform, well, do that instead of using the abstract machine. So
yeah, true. Well, that wasn't the purpose of the talk, of course, but we do have a study group, SG12, that works on undefined behavior right now and is trying to reduce the cases where it occurs. So there are things where there will always be some, I guess, but we are working on reducing them. Such things as doing a mem copy to some storage, which could be undefined, but could also give birth to an object, say some casts which are improper, but kind of makes sense to programmers. Why not give them a meaning? There are things we can do with that. And as we were saying, indeed, given that we have a language that lets us do, if we want to, zero-cost abstractions, we can actually use that. Why not? There are people in the room right now who are working on floating fixed-point numbers and doing very efficient stuff and defining behavior as much as they can. If you want exceptions all over the place, nothing is stopping you, of course. You can use vector at if you're a very strange person. Or you can actually use the tools that will remove that for you, using the range for loops and everything. They will probably remove all of those bugs from your code in the first place. Modern C++ really reduces the number of cases you have to look out for. So yeah, I agree with you. Library solutions are probably better than the abstract machine. I doubt we will change the abstract machine to please those people. It would be counterproductive from a C++ point of view.
All right.
Anything else? Thank you all for coming. You're very nice.